With this understanding of the general nature of the atom, of matter, the stage was set for the final conceptual jump in this inductive phase of the original project. In the work that I had done in some 20 years or so up to this time, I had arrived at some rather interesting mathematical expressions connecting some of the physical properties of matter with the atomic numbers. Now what I had to do was to connect the atomic numbers to motions. This was another long and difficult task. It was very often a frustrating task. But it finally dawned on me one day that one of the most interesting of these expressions, one that connected the interatomic distance in the solid state with the atomic number, could be very easily and simply explained if I assumed a general reciprocal relation between space and time. Now, those of you who are encountering this idea for the first time may find it rather weird. So did I. I can quite understand how you might feel that way. In fact, when I first thought of it, the idea of the reciprocal of space struck me as about as reasonable as the idea of the reciprocal of a soft-boiled egg. But when I took a second look at it, it wasn't so unreasonable after all. The only relation between space and time of which we have any actual knowledge is motion. And in motion, space and time are reciprocally related. So, of course, having come that far, I had to go on farther and see what else I could put this relation to use with. And very much to my surprise, it was almost immediately evident that this relation gives us the answers, simple and logical answers, to no less than half a dozen of the long-standing problems of science. Now, any of you who have ever done research work will realize that this is the kind of a breakthrough that we see in our most rosy dreams. And obviously it called for an immediate start on a full-scale investigation to see how far this would go, how far this clarification of the physical picture would extend. By the time of my first publication in 1959, I had arrived at a set of two postulates from which it's possible, I showed it then that it was possible to derive the principal features of the major branches of physical science by pure deduction without any supplementary assumptions or without drawing on anything from experience. In the meantime, the members of this organization that are meeting here today and other scientists around the world have joined in this effort. And we have extended the scope of the theory to the point where we now feel fairly confident that we will ultimately reach the goal that Newtonian scientists were aiming at and couldn't quite make. That is, a general explanation of the physical universe. I think at this point I'll have to dig into some of my lubricant here. The voice seems to be going bad. When I was here in January down Provo, I lost my voice altogether and had to talk for 2 days with practically no voice. So if I lose a little bit of it now, we won't worry about it.
Sound system is good enough that you can tone down the stage.
Okay. For those who shudder at the thought of having to reconstruct all of their scientific ideas, I want to say that probably 90% of what passes for scientific knowledge today will be incorporated into our new system without any significant change, other than perhaps in the language in which the ideas are expressed. Another 5% will take only a change in the interpretation of the mathematics, because the mathematics is okay. And it's only 5% or so that we'll have to reconstruct. And those items are practically all in these, what I call the far-out regions. The regions where science is having plenty of difficulty now. On first consideration, it may seem rather strange that such a radical change in the basis of a science would make so little difference in the results. But there's a very simple explanation of that. The 90% that I'm talking about was not derived from these inventive basic theories of Einstein and others. That 90% was derived empirically. The theories that are included in it are the inductive theories of lower rank that I've been talking about. Now, what we have done with our new development is simply to give a inductive basis to which we can attach this 90% of inductive theories of the lower rank. And then, of course, we can go in and take care of this 5% that has to be reconstructed. Now, having gotten that far, our problem is to bring this work to the attention of the scientific community. And there, of course, we meet the same thing that all innovators do: a reluctance to look at the results. Those who take only a superficial look at them simply throw up their hands in horror and say, "Good Lord, these people disagree with Einstein. They must be crazy." Well, in all the poking around I've done in science, I've never yet found a natural law that says anything about prohibition and disagreeing with Einstein. But as long as that's such a popular idea, I think we ought to take a look at it and see just where we do disagree with Einstein. Whenever comments of that kind are made, they refer invariably to relativity. Einstein had other ideas, some of which we agree with, some we don't. But it's relativity that is the central issue. In fact, it's the central two issues, because there are two relativity theories that don't agree with each other. There's the special theory that applies to uniform translational motion, and there's the general theory that applies to accelerated motion. Now, here's the way the relation between the two looked to Peter Bergman, one of our foremost men in the field. It is quite true that the general theory of relativity is not consistent with the special theory any more than the special theory is with Newton's mechanics. Each of these theories discards, in a sense, the conceptual framework of its predecessor. So it's impossible to agree with both of the theories fully. Actually, the general theory doesn't rate particularly high among the leading physicists of the day anyway. Thank you. the first aid here, maybe I can go on for another half hour. Maybe it's a good thing I left out the first half hour. As an example of these comments about the general theory, here's one from Bryce DeWitt, who was one of the leading investigators in the gravitational field that the general theory is supposed to cover. He says this: as a fundamental physical theory, general relativity is a failure. P.W. Bridgman predicted this: the arguments which have led up to the theory and the whole state of mind of most physicists with regard to it may someday become one of the puzzles of history. So I don't think we need to worry much about disagreeing with the general theory. That's a general disagreement. Special theory is another matter. And whether or not we agree with or disagree with the special theory depends on what's in the theory. Quoting Bridgman again, there is a tendency to define the content of the special theory of relativity as coextensive with the content of the Lorentz equations. P.K. Feyerabend, who was one of our prominent philosophers of science, says it must be admitted, however, that Einstein's original interpretation of the special theory of relativity is hardly ever used by contemporary physicists. For them, the theory of relativity consists of two elements: the Lorentz transformations and mass-energy equivalence. On this basis, we don't disagree with the relativity theory at all. Now that's the situation with respect to the theory as a theory. But where we do come to some disagreement is that we cannot accept all of the unsubstantiated inferences that have been drawn from the theory. A good example is the question of the existence of speeds in excess of that of light. It's generally believed that a speed limitation exists by reason of the mass-energy equivalence. And that, of course, has been demonstrated in the atomic bomb and in a great many experiments. In those experiments, a certain quantity of mass is converted into a certain quantity of energy. And the original particles that entered into the reaction have suffered a loss of mass. The uranium atom is no longer a uranium atom. But the mass-energy equivalence that is supposed to exist in a fast-moving particle is an entirely different process. There, the particles are supposed to exist as before, and a part of the energy that's imparted to them is supposed to manifest itself as an additional mass by some unspecified means. So those are two totally different processes. And consequently, we cannot use the demonstrated existence of the atomic bomb and other processes of that kind as evidence in favor of the presumed increase in mass at high velocities. But we do have another piece of evidence that's relevant, and that is that if we accelerate a particle to high speeds by means of a presumably constant electric force, then the acceleration does not stay constant, as it should on the basis of Newton's law, but drops